So welcome back to our last but not least presentation of Sergio Prado from Embedded Labworks, and he will tell us something about porting and running up a OpTE on ARMv8 devices. So, Mr. Prado, your audience.
Thank you very much. Hope you all are enjoying this session. So we already had 2 sessions about TE and TrustZone. This one will be focused on ARMv8. So TrustZone for ARM8 based devices, so processors especially running Linux. So we're gonna have a little bit of introduction on TE, and we're gonna talk about a little bit of the history of OpTE. It's an open source TE implementation. We're gonna have a quick overview of the internal workings of OpTE and also TrustZone to understand better how it works. And then I'm gonna talk in the end a little bit about how to port in general OpTE to an ARM Cortex-A device. If we have time in the end, we will have a little bit of demo on OpTE running on one of the ARM platforms that I have here. If not, I want to just mention it. So yeah, let's start quickly. So my name is Sergio Prado. I'm Brazilian. I'm currently working for Toradex, so I'm team lead at Toradex. I'm helping them develop an operating system called Horizon Core for embedded devices. I have also my company called Embedded Labworks, where I do a little bit of consulting and training, and I try to contribute with open source software. So I'm kernel Linux developer and contributor, and contribute to other open source projects like BuildRoot, for example. So let's start. What is TE, or Trusted Execution Environment? The idea of TE is that you want code and data to be protected in terms of confidentiality, privacy, and integrity. So you want that no one will have access to the data that you are dealing with, and also you want to make sure that you're running the code that's supposed to be run that device. And we may be not aware, but there are a lot of devices out there that it's using today a kind of TEE implementation or a TE operating system. So most of the smartphones, smart TVs, I would say that most of those consumer devices today are running some kind of TE as another measure to mitigate risks on the assets that the vendor wants to protect. So this talk, as I said, is going to be a little bit about TE, and of course we'll be focused here on OpTE. But why we need TE, right? Why we need this trusted execution environment? If we think about devices built with an operating system, a kernel like Linux, we have millions of lines of code, right? And that means statistically, we're going to have lots and lots of bugs. And we cannot make sure that with tests, we can spend months and months on tests, but we cannot make sure that we are not shipping a product with bugs. We will be doing that, especially on those devices that are running a kind of Linux flavor or an Android flavor. And again, we can mitigate those risks trying to find the bugs, but in the end, we will have bugs in the final product. And if those bugs expose some kind of vulnerability, that vulnerability could be exploited, and that could be a problem for your product. So one idea to mitigate this risk is to run applications in a way that it's isolated from the assets that you want to protect in your device. That could be code, or that could be your data. And there are a few approaches for that, right? You can run virtual machines in your device, but for embedded device, that's not so far. That has not been done so far in embedded devices because of research usage, right? So running your applications inside virtual machines, full virtualized environments. One way that we could do that is using containers. So running applications in a containerized way could be an idea. And that really improves the security if you configure the containers in the right way. But one problem on using containers is that the kernel is shared between all of the containers running the device. And if you have bugs and vulnerabilities in the kernel, all of the system will be compromised. So one way to mitigate that risk is that you would run all of the important things, the things that you want to protect, you would run in a separated and secure environment. And that's what we call TE. So in terms of terminology, basically we would separate the applications in two roads. We have the secure or trusted road where we run trusted applications, and we have the unsecure or the normal road where we would run untrusted applications. And the main idea here is that there is some kind of feature in the hardware that would make that possible, where you would isolate hardware from the secure road to the unsecure road. So the secure road would have access to hardware that could be buses, peripherals, memory, that the unsecure road doesn't have access to. So TE is really a kind of execution environment. Could be a full-blown operating system, just a scheduler, or just a small bare metal firmware dealing with things that you want to protect in your device. So that's basically the main idea, right? So here in the left we have a non-secure road or a normal road running, for example, Linux or Android with all of our applications, and on the right side, we have the secure roads where we would run our trusted applications. And some kind of hardware would provide this kind of isolation between the both roads. And with CTE, we can do a lot of things, right? So we can protect sensitive computations like cryptographic operations, generation of keys, things like that, or authentication, right? Dealing with authentication. We could provide some kind of secure storage for the device where you could like store your private keys, uh, uh, encrypted data. For example, if you have an application that has DRM content protected by digital rights, so you could make it possible to store those data encrypted. And if you have some kind of resource in the hardware, for example, a secure that data path in the hardware, you could use it to make the secure road to send all of those data directly to the device, for example, a graphical card or an audio device, without dealing with this data in the non-secure road. So if you have some vulnerability in the secure road, an attacker will not be able to read all of your data, right? That could be, for example, content, a DRM content, because the attacker doesn't have access to the secure road. Now, how to implement a TE? Again, we need the hardware for that. So we need a mechanism to isolate the hardware, right? And that's why we have, for example, ARM TrustZone. And there are other implementations of this kind of hardware isolation. For example, RISC-V Smooth Zone is another implementation. So in a nutshell, how ARM's TrustZone works. And here I'm really focused on ARMv8 devices, so ARM Cortex-A 53, for example. Although, if you think about Cortex-A in general, for example, Cortex-A9, ARMv7 devices, it's very similar. So in ARMv8, we have at least 3 execution modes: user mode, kernel mode, and hypervisor mode. A typical system running Linux, of course, you're going to have applications running in user mode. that they call EL0, execution level 0. We're going to have the kernel Linux running in kernel mode, EL1, and usually don't have an hypervisor in an embedded device running Linux, but we could. That's why we have a mode for that. And ARM TrustZone introduces a new module called Secure Monitor Mode. So that is fourth mode there that will handle this transition between the normal world and the secure world, right? And in practice, it's basically one bit in a register. So there is a register and there is one bit there. If this bit is 1, you are in the normal world. If this bit is 0, you are in the secure world. That's it. What happens is that there is a system call called SMC, Secure Monitor Call. That's when it's called, it will do this transition, right? It will change this bit, do this transition from the normal world to the secure world, and vice versa. So the transition from the normal world to the secure world on TrustZone for Cortex-A devices is done via this special instruction. So that's what this diagram is showing, right? So we have applications running in the non-secure world that wants to request services from applications that's running in the secure world. The application will need to talk to the kernel and request the service, and the kernel will call the SMC instruction and request the service to the implementation of the secure world. That's basically in terms of how this transition from the secure world to the normal world and vice versa happens. So there are a lot of implementations of TE. Here we have a few. I know two from Samsung, Knibi, Integris. There is the QC from Qualcomm, I Trust from Hawaii, Trust from Google, and there is the open source implementation now from trusted firmware organization and Linaro, call it OPT. That's going to be our focus from now on in this presentation. If we think about it, right, the main idea here is that you have applications running in the secure world that will request services from applications running in the secure world. So the non-secure applications will request services from applications in the secure world. We have a hardware feature to implement that will isolate hardware for us, but we need also a definition in terms of software to make that code portable, right? So there is an organization called GlobalPlatform that defined a set of APIs that can be used to implement a TE. So if you are using a TE implementation that is based on the GlobalPlatform TI, that means GlobalPlatform API, that means that you will be able to port easily your applications to other implementations of TE that is based on the same standard. And OPTE follows this GlobalPlatform API standard, both for the libraries, both for the API that non-trusted applications would use, and for the internal API that secure applications would use. So now OPTE. OPTE is an open source implementation of a TE for TrustZone based devices and ARM Cortex-A running Linux. It's BSD license, so it's very permissive in terms of license. It was created several years ago by ST Ericsson, and then it was maintained by ST Microelectronics. Then in 2014, Linaro decided to start working with ST Microelectronics to open source OPTE. In 2015, it was open sourced and the ownership was transferred to Linaro. 4 years later, the ownership was transferred to the Trusted Firmware Organization. But still, Linaro is doing a lot of things with OPTE. So OPT is this T implementation, open source T implementation for devices running some kind of Linux flavor on ARM Cortex-A devices with TrustZone. That's basically it. And OPT also implements the two APIs from GlobalPlatform, the client library for untrusted applications and the internal library for the trusted applications. So those are the main blocks of OPT. Of course, we need the hardware with a TrustZone enabled for ARM Cortex-A. In terms of firmware, for ARMv7, there is no requirement, but for ARMv8, we need the ARM trusted firmware implementation that will provide boot time and runtime services. And we work in conjunction with OPT. Now OPT itself, it provides the client library. It provides a daemon, a user space daemon for the OPT OS. Those libraries and daemons will run in the non-secure road. We have a kernel driver, a Linux kernel driver that implements the communication with the monitor. And of course, we have the OS implementation, both user space and kernel space. And on top of that, we run applications, right? Untrusted applications and trusted applications. So this is the main architecture of a device running OPT. We have a rich OS, for example, running Linux or Android. So what we have here in green is what is implemented by OPT. So we have the client implementation running in user space in the untrusted or normal road. The client library is based on the GlobalPlatform API, and the applications will use this API to talk to applications in the trusted road. And this small demo, the TE supplicant, will provide some kind of services for the OPT OS. So when the OPT OS wants, for example, to store files in the file system, here we don't have any kind of drivers for file system to talk to storage devices. It will need to talk to the normal road. So there is a protocol and a communication that will happen with this daemon, for example, to provide this kind of feature for the OPT OS. In the kernel, we have the T subsystem and the T driver that will be responsible to communicate with the OPT OS, right? And here we have the trusted firmware for ARMv8 and also the OPT implementation in kernel space and the applications running in user space with a library that is also based on the GlobalPlatform API. So all of this in green is part of the OPT implementation. If you want to try OPT, it's very simple. You can even run on QEMU. If you have a hacker board like Raspberry Pi, you can also build for the Raspberry Pi. If you don't have any hardware that is currently supported by the project, you can just do a QEMU build and try it. It's very simple. The build scripts are based on build root. And this link will provide all of the information you need to do a build with OPT and try to and then you can run untrusted applications and trusted applications and see how it works. This is in a nutshell the commands that you would run to download the source code and build. Here I'm downloading the source code for a platform that I have here from Trodex called Verdi. It has a SoC from NXP called IMX M Mini. So it's a Cortex-A device with TrustZone, and it is currently supported by the upstream project, so I can just download and run without much effort. And that is basically the process. The project is composed of different repositories. So here we can see this is the manifest file with all of the different repositories. We have the client repository with the library for client applications, for untrusted applications. We have the OS itself. We have test applications and examples. We have the build script. So all of this are in separated repositories. And of course, we need the source code for the bootloader, then kernel. So after we run these two commands, repo init and repo sync, we're gonna have the all of the source code to do a build, and then it's just a matter of running make tool chains and make to do a build for the device that you selected in the manifest file. In the end, we're gonna have the images to boot the device. Here we can see, based on the output of this build, this will vary between depending on your platform, right? It's very dependent on the platform. Here we can see that we have the root file system for the device, we have the kernel, we have the device tree, and we have this file called flash.bin. Basically, inside this file, we have all of the boot artifacts to boot this device. So inside of this file, we have the SPL, that's basically the first stage bootloader. We have the ARM trusted firmware to start the boot process, and we have the TE itself, and also U-boot. That's our one of the latest bootloaders that will run before starting the Linux kernel. Here we have a basic representation of the boot process on ARMv7 and also ARMv8 device. So when you are not using TrustZone and all of this TE implementation, basically everything will run in the secure road, right? Because no one is changing to the normal road. So usually that's what's happened. So you have a run code SOC that we call SPL, that we call U-boot or bootloader, that we call kernel, that we mount the boot file system. Now, when you switch to a device running OpTE, then OpTE and for ARMv8 also ARM Trust firmware will be responsible to do the switch from the secure road to the normal road, and then start the normal road artifacts. That would be, in our case here, U-boot and the Linux kernel. After boot device running OpTE, you can just check if the TE supplicant daemon is running, and you can run some demo applications. There are some very nice demos that you can try. For example, this hello world that would just make calls from the unsecure road to the secure road, incrementing secure variable. Now, porting OpTE, you will need to do changes in the normal road, in the secure road. For the normal road, you're going to have to build your kernel with TE support and the TE OpTE driver enabled, and you're going to have to build your file system with the client library, libTE and also the TE supplicant daemon. Now, for the secure road, you're going to have to port OpTE for your device. Porting OpTE, the effort to port OpTE, it will depend on your device and your SoC. I'm going to talk a little bit about it. There is some kind of memory requirements to run OpTE. OpTE itself will need at least 256 kilobytes of RAM to run, and very small, right? To manage the secure road. And there are usually in those SoCs, there are two options. You can use the SRun inside the SoC. So usually those SoCs have static run inside of it that you can run any code inside there. And you could use SRun for that. But sometimes the SRun is small. Let's say you have 16 kilobytes of SRun in your SoC, then you will not be able to use it for OpTE. Then you need to share your main run device. So for that, there is a controller in the SoC that is also part of TrustZone, called TrustZone Address Space Controller, that will make it possible to protect part of your dynamic run, of your external run, from the normal road. And this is currently supported in OpTE, so you can use that. You will also need to kind of share part of your memory for communication between the normal road and the secure road. I'm going to show you in a few minutes how this is done in an include file in OptE. So this is the OptE source code where we have all of the ported platforms. We can see here basically it's a directory per vendor or SoC, right? TI, IMX, and inside there we have the port for that platform or vendor. Basically, to port OptE, you're gonna have to change or create 4 files. That's the basic uh, implementation for the porting, right? You have, I can quickly show here, we have one file where you would do configurations on OptE, kind of how many threads that you want to be running parallel in OptE. It's important to say that OptE doesn't have an scheduler, so it will basically use the Linux scheduler, right? So when application running in user space in the unsecure road call a service in the Linux kernel to request something from the secure road, you will do IO control, then the Linux driver will execute an SMC instruction, and basically here we have a transition from the unsecure to the secure road, right? But the execution context continues, so you don't have anything running in parallel inside the unsecure road, right? And you could have interruptions in the middle, the code would be interrupted, and it will run until the end, right? So if the trusted application blocks for some reason, it will block all of this process until it returns, right? So there is no parallelism here happening. In this file, so we have some kind of configuration for OptE. We need to define also some functions that will be called to basically do some setup in the hardware. You're going to probably want a console, and then you have include file where you would configure the run, right? Which part of the run you want to use as OptE run, protected OptE run, which part of the run you're going to use to share and do communications between the process. And that's basically the idea. Of course, to real protect the device, there are more things to do. There's basically the list that I come up with things that you need to do to protect the device. 2 things that I would like to mention here. Secure boot is very important because if you don't have secure boot, an attacker could just replace the OptE implementation and then your security is gone. The other thing that is important is to have a hardware unique key. If you don't have a hardware unique key in your device, OptE will use this hardware unique key to derive all of the other keys that will create. So if you don't have this hardware unique key, that's basically a key that's somewhere in the hardware that's not accessible from the software. If you don't have that, your security will also be compromised. So, for example, on IMX and XP IMX devices, we have a secure module called CAN, and this secure module provides this hardware unique key. If you don't have something like this in your SoC, you could think about using a secure element or a TPM or any other kind of hardware implementation to have this hardware unique key available for OptE to secure the device. You're gonna need hardware random generator, secure clock as a source of time. If you don't have that, again, your security will be compromised. And to conclude, OptE, it's a very nice implementation open source for TE, but that's not enough, right? It's just one more way to improve the security and mitigate risks in your product. So I hope you enjoy this presentation, and yeah, I'm looking forward for questions in our question and answer session. Thank you.
Thank you, Sergio, for a very interesting and deep look, like how we can, in a practical way, set up the environment. So we will now prepare everything for the Q&A session. So my request also to the audience, please use the Slido. We have had a couple of very interesting talks from great experts here. So use this opportunity to bring in your own questions. and then we will start in 1 minute with the Q&A session. Thank you.